and good morning, everybody. So, what I want to present is a joint work with Maxence Cassier and Alex Rosas. But before entering the subject of the talk, Maxence asked me to give a brief recap about mathematical models for dispersive electromagnetic media. And this introductory part will be based on the article we wrote with Marina Kachanowska, and in which, in particular, we gather various results from the literature. This is a non-exhaustive list. And I realize that there will be some overlap with the introductory talk of this conference, but I think it's not so important. Okay, so let me first recall the convention that we shall use for time Fourier transform, which is the one which is commonly used by physicists, and it is the one for which, when you consider a causal field, which is reasonably bounded at infinity, then its Laplace Fourier transform is then analytic in the upper half plane. And I will use this. So Maxwell's equations first relate the time derivatives of the electric and magnetic inductions to the corresponding curls of the fields. So these are two equations, and two additional equations are needed, and these are the constitutive laws of a given material. And in a standard dielectric medium, this is a simple proportionality law with a constant epsilon and mu, which are real and positive, which are called the permittivity and the permeability. And in the case of dispersive medium, it is essentially the same, but in the frequency domain. I mean for a Fourier transform of the fields. And now the permittivity and epsilon and mu are complex valued functions of the frequency. And this is the main difference. Okay, so what is usual is to make appear this constitutive law as a difference with what they would be in the vacuum. So in the vacuum, epsilon would be epsilon 0, mu would be mu 0, and the difference are represented by two vectors, which are called polarizations and magnetization, respectively. And of course, these two vectors in the frequency domain are also proportional, respectively, to E and H. And it's simply another way to represent the constitutive laws via the notion of susceptibilities, electric and magnetic susceptibilities. And there are some requirements of, let's say, of physical nature that we can translate into mathematical terms that are needed. The first one is the fact that at very high frequency, the matter will behave as a vacuum, which explains these high frequency limits here. The second one is the causality principle. We want that both fields and inductions remain causal fields. And related to what I said at the beginning, it means that epsilon and mu will be analytic in the upper half plane. The what's called reality principle, we want that when we come back to the time domain, the fields and the inductions remain real valued, and this imposes this symmetry that each time you apply a symmetry with respect to the imaginary axis, each coefficient is transformed into its complex conjugate. And so in time domain, if you assume that the inverse Fourier transform of the susceptibility, for instance, are locally integrable functions, this quantitative law can be rewritten directly in the time domain with convolution, which means that memory effects are generically present in this type of medium. Okay. So this is finally the system you have to deal with. And there is a last concept that we heard about, and that I will define in a precise way here. It is the concept of passivity. It concerns the case where you want to look at the evolution, the free evolution of this system in the whole space, for instance. And so you define the electromagnetic energy in this way, as it is in the vacuum. And you will say that this medium is passive in the physical sense if the energy that may vary in time, it's not necessarily decreasing, but what you say is that it will never exceed the value that it had at the time t equals 0. So in some sense, this type of system cannot bring energy to electromagnetic waves if there is no source. Okay. And from this, if you go to the frequency domain, it is easy to see, it's essentially a question of applying Palais-Wiener and Plancher's theorem, that a sufficient condition for passivity is that both functions omega times epsilon and omega mu are Herglotz functions whose definition is recalled here. So generally, this is the way that passivity is expressed in many papers, but for us, there is an open question or a conjecture, I don't know. Is there equivalent? So is this condition here is necessary to have a passivity in this sense? And I will come back on this later. Okay, among all these families, there are a large class of models that are provided by rational fractions, and these are generalized Lorentz media, which are given by expansion of this type, where all coefficients that appear here are real. The coefficients small omegas are, we call them the resonances of the medium, either electric, either magnetic. And the alphas here, which are positive, are what I will call the damping parameter. So when all alphas are 0, these are not dissipative Lorentz media. And in particular, the presence of these terms makes that as soon as one of the alpha is non-zero, the corresponding pole of the element is not on the real axis. So the corresponding convolution kernels are, of course, easy to express. And depending on the amplitude of alpha with respect to the corresponding resonance frequency, you get either a damped sinusoid, as illustrated, or a sum of two decreasing exponentials. This gives something like that, which is the case. Oh, merde. It's French. It's French. So what I say and what you see is that the kernel, it's a remark that this kernel is never monotonous with respect to time. And moreover, if one of the alpha is 0, you see that it will not decay at infinity because there are non-damped sinusoids. Okay. You can rewrite Maxwell's equation in such a model as an augmented Maxwell system as follows. So what you see here, in fact, it's difficult to push one of the buttons without, maybe it depends on the size of your fingers. I don't know. Okay. So here you would have the Maxwell's equation in the vacuum, and you see that these are coupled with auxiliary unknowns. Each unknown is attached with one of the elements appearing here, and is itself related to the magnetic or electric or magnetic field through an ODE, which is of damped harmonic oscillator type. Okay. And this is completed by initial condition. Okay. Which is, so the auxiliary unknown vanish at time 0. And it is so these functions satisfy the Herglotz property I mentioned before, but there is another way to recover passivity via energy identity. And so I introduce a total energy, or a Lyapunov function, reason why I call L, as the sum of the electromagnetic energy I defined previously, plus an additional energy. And the additional energy is the contribution of the auxiliary unknowns. And what is easy to establish, so note that at the initial time, since the additional energy is 0, both total and electromagnetic energy coincide. And I also introduce what I will call the damping function, which is a similar quantity, but that involves, this time, the damping parameters. And which is easy to deduce is an identity. So I will not explain. You multiply, I will not, in fact, I will explain. You multiply by E and H and integrate and add the results, and you get what I'm saying. You have this identity. So as D is positive, as you see, it means that L is decreasing. So L is less than L of 0, which is E of 0. And since this additional energy is positive, it's larger than the E. So you see that E of t is less than E of 0. So this corresponds to the definition of passivity I gave. Okay. So I want to mention an alternative approach to passivity directly in the time domain. And what we try to do is to mimic what was done in the 90s, essentially, by a lot of Italian people, for instance, in the context of viscoelasticity, and their objective was to obtain directly in time domain energy estimates. So typically, what you have to deal with is quadratic quantities of this form. Okay. And for instance, just to have an idea, if k is a kernel k, is a Heaviside function here, so this is formally a Dirac, so that this is u prime u, and u prime u is a derivative with half factor of the square of u. So the idea, what becomes such an identity for a general, the question is, what becomes this identity for a general kernel? And the result is this one. And what is important to see is that it is a derivative in time of essentially a sum of squares plus another sum of squares. And this is a basic identity that we can use to analyze this. And I will directly write the energy identity we obtain by this way. So it is useful for this to introduce the time primitive of the field that I indicated with an index P, and it is a primitive that vanishes at 0. And the energy identity is formally of the same form that for the one for Lorentz meridian, except that the D and E and additional energy are completely different. And these are given by this expression, which looks complicated, which are complicated, but which are essentially sum of squares, as you can see. Not surprising, so I'm going to rewrite here this way. And you understand that in order to conclude to passivity, you have only to ensure that this energy is positive and this damping function is positive. It's really a damping. And for this, you are simply to ensure that all coefficients that are in front of squares are positive functions. And so what you deduce is that passivity is ensured as soon as for each of the kernels, the initial value is positive, because of this here. And the signs of successive derivatives alternate along this, according to these three inequalities. So this is not clearly satisfied by generalized Lorentz model because, in particular, this implies some monotonicity, and which are not. I mentioned that it was not satisfied by the kernels. So this does not apply to Lorentz models, but this reminds us more or less the notion of completely monotonous functions we heard about yesterday, except that we ask only the sign alternance up to the third derivative. And so I have a kind of question for the audience. Can we find, so this is sufficient to ensure stability. Is it possible to find a function that satisfies this without omega times k being an Herglotz function? If there exists such a counterexample, it will mean that there is no equivalence between the passivity by Herglotz and the definition. Okay. But we even go further, and it is a transition to the main part of the talk. You can also deduce what I call exponential stability. If in addition to the above, you assume that the initial value is not only positive but strictly positive, and that these three functions are not only positive but also comparable the one to the other. So this sign means that the equality holds with up to a multiplicative constant. Then what you see is that, for instance, because of this, you can control this part of the energy by this part of the damping function. If you have the first inequality here, you can control this part of the additional energy with this part of the damping function. And the same for the last inequality. So when you have that, you can show that there is a constant delta, so that L is less than a constant delta times D. And if you substitute it in the energy identity and you use a Grunwald's argument, then you prove that the energy decays exponentially in time, and this is what is called exponential stability. Okay. And just to finish, no, not to finish, if it is finished. Okay. So the objective of the talk is to consider the Cauchy problem, but this time for Lorentz media, and to ask the question, which is a natural question for dynamical system. Does the energy tend to zero for large time? And if yes, what is the convergence rate to zero? Ah non, oui, alors voilà, c'est un transparent qui est mal placé. So there are some results in the literature about this question. To begin with, a result by Figotin-Schenker, which concerns a very abstract and general evolution model, but when you specialize it to Maxwell's equations, you realize that it can apply to the case where there is only electric susceptibility. And the important function that enters in their result is a function we have seen several times. It is the imaginary part of the function omega times k, which is seen as a limit from the upper plane that I will call the electric gamma function. Okay. And so the result is that if this function is almost everywhere strictly positive, and so it is, in the sense of Lebesgue measure, it may vanish at some points, but in such a way that the inverse remains locally integrable. So it's rather constraining. Then they prove that the energy goes to zero. I will not enter too much in how they do that because it's complicated. It's quite abstract. And in some sense, it relies on an augmenting Maxwell formulation of Maxwell's equations. which is based on the representation of Herglotz functions. And in their augmented formulation, there is a big unknown of vectors, where the first two components is electromagnetic field, and you have additional unknowns that are themselves functions of an additional space variable, let's say xi. And the additional equations that govern the additional unknowns are ODEs in time, which are parameterized by xi. And the augmented system is of conservative type. It is a kind of Schrödinger equation where the operator is self-adjoint. And thanks to that, they can use a spectral theorem to get an integral spectral representation of the solution. And when they reproject on the electromagnetic field, using a Riemann-Lebesgue type argument, they prove the unfortunately, when you want to apply this for Lorentz model, you realize that it works only if there is one term in the expansion whose resonance frequency is 0 and the corresponding alpha is strictly positive, which is a dissipative Drude term in the expression, in the expansion. So it is not satisfied for most Lorentz model. And moreover, the question of the rate of decay is not addressed in this work. This question has been addressed by a series of papers by Selznickes and his collaborators. And this is the result. So first I introduce, so the gamma is the same gamma electric and gamma magnetic functions. So the first assumption looks like Figotin condition, except that it must be strictly positive everywhere, and it must not decay too far at infinity. Okay. This is the first set of conditions, and another set of conditions is done directly in the time domain on kernels. And you say that it says essentially that the kernels, the derivative of the kernels, decay exponentially fast at infinity. And with that, they're able to prove that, provided some regularity, H1 regularity of the initial data, the energy goes to 0 is 1 over T. So in the language of control theory or stabilization theory, this is called polynomial stability because this is a polynomial, as opposed to exponential stability I mentioned previously. Okay. So, which is funny is that the proof uses again an augmented formulations of Maxwell's equation, but which is not the same. The additional unknowns are function of another time variable. So there is a second time, if you want. And the additional equations you had are no longer ODEs, but transport equations in the ST plane. And for those who know, it is used, it's based on the trick proposed by Ida Fermos for treating convolutions through the notion of cumulated path system. The difference with the previous case is that this time, the operator is no longer self-adjoint. So you cannot use the spectral theorem, but you can conclude with using black box theorems from semigroup theory. And in fact, these assumptions are used to satisfy the assumptions of the abstract theorem. Okay. So when you apply this to Lorentz model, you see that this work, provided that all the damping coefficients are strictly positive. And this is why this is what I will call the strong dissipation condition. Of course, you see that it is needed because if one of the alpha is 0, then there is no decay of the kernel. And I will oppose it to the weak dissipation assumption, which says that only one of these coefficients is strictly positive. Okay. So now I enter into our work, and I will present two approaches to the stability theory. The first one I will call a frequency-dependent Lyapunov function method. You will see that the interest, it is a self-contained. You do not need to use complicated theorems. It's based on elementary tools, but some ideas are a little bit tricky, to be honest. And it works in the context, it permits to recover the results I just mentioned. I mean, it works only under the strong dissipation assumption. And in the second step, I will present an approach, modal approach, which is a little bit more physical, so a little bit more comprehensive, and which gives optimal results. In particular, we shall be able to extend the results to only the weak dissipation assumption. So the only disadvantage, if you want, is that it's technically and computationally involved, a little bit involved, in particular because you have to deal with non-self-adjoint spectral theory. Okay, so first the time-dependent Lyapunov approach, and I will explain the idea only in the case of the Drude model. So it means the case where there is only one element in the expansion, and the order 0 term, the resonance frequency is 0. Okay. So in terms of PDE, it means that you have only one P, one M, and in the ODEs, there is no zero order term. Okay. This is more simple. And what we are going to do is to apply Fourier in space. Oh. And by frequency dependent here, I mean, in fact, the space frequency. So what I call frequency is the modulus of the K, the dual variable of X. So if you apply Fourier transform to this, you transform the PDEs in a family of ODEs parametrized by K. And what we are going to do is to perform energy identities, but at fixed frequency. Okay. So the idea is that simply you multiply in the scalar product sense the equations by E, H, P dot, M dot, and you add everything. And what you get is a spectral analog of the energy identity I presented before. So this was the L, if you prefer. So here, this is what I will call the spectral energy density. So it is the density energy at frequency K. Here is the augmented energy or additional energy, associated to P and M. And you have the spectral damping function. Okay. And the reason what this is not sufficient is that you are not able to control completely the total energy with the damping function. Because we assume we are in the strong dissipation assumption, so both alpha E and alpha M are positive, you see that you can control this by this. So you can control the second part of the energy by the damping function. But the problem is to control E, that does not appear in the damping function. So what you can do is to use the constitutive laws. And thanks to that, you can say that the energy you want to estimate here, the first part of energy, which is less than the sum of squares of E and H, you can control, of course, by these two sums of squares. And the first sum of squares is controlled by the damping function. And then the problem is to control this second order derivative. And this suggests to use the same energy identity, but for the time derivative of the solution. Of course, as equations have coefficient independent of time, it is clear that you also have this identity, which is exactly the same as before, except that now I consider a first order energy where you have time derivatives that appears here, and an additional energy when you have double derivatives instead of simple derivatives, and the same for the damping function. So why is it interesting? Because these times you can control what was missing with the new damping function. Also, you can control this additional energy with this damping function for the same reason as above. But the problem is shifted to this. You have shifted the problem. Okay, so and if I summarize what I have obtained up to now, is this. You have two identities, two energy identities, two damping functions, and everywhere I am able to control the energies by the damping functions, except maybe the energy of order 1, which is the control of E dot and H dot. And this is where I am going to use Maxwell's equations again. And this is where we are going to lose uniformity in K in our estimates. For instance, so this is one of the Maxwell equations. If you want to use this to control E dot, you see that you make appear a power K square in factor of a term that you know already know how to control. Okay? It is like that. Because this is present in the damping function. If you do that with these other Maxwell's equations, what you obtain is a control of the first order energy in a similar way than the second, the zero order energy, the density, but up to the price of the apparition of the factor 1 plus K square. Okay. So to gather everything, so we add the energies, but instead of making a simple addition for homogeneity reason, because this energy involves time derivatives, we renormalize it by this factor 1 over 1 plus K square. So this is a homogeneous quantity, and you do the same for the other functions. And by linearity, of course, for this cumulated energy, you have this identity. And from what I explained in the 2 slides above, is that you have a lemma which says that these times you are able to control the cumulated energy by the damping function up to a factor K square. And the consequence is that, so I will come, I will not come back, I already proved this. So if you substitute it into the identity and you use Grunwald's argument, you get an exponential decay. So here only because this quantity, this quantity at t equals 0 is 0. So you have this. Of course, this controls the energy we are interested in, or the energy density we are interested in. And this is, because of the normalization, you can prove that this initial energy is controlled by the energy itself of the initial data. So it means that the energy density decays exponentially, but with a rate that depends on K. So when you come back to space, there should be a title. When you go back to the finite estimates, first to estimate the energy, you integrate, like Plancherel, you integrate about all possible Ks. You use exponential estimates that I just obtained here, and then, a simple manipulation. You multiply and divide by K to the power 2s. K is 1 over square root of 1 of plus K square. And you also multiply and divide by T to the power S. And which is, so we S some S positive. And which is important here is that you make appear a function which is only a function of the ratio T over K square. Okay. Which is this. And this function is a function r to the s times an exponential. So typically, it has a shape like that. It begins at 0 and go at 0 at infinity. So it would be for s equal 1, for instance. And in particular, it is a bounding function. And if you extract the upper bound from the integral, you make appear the Sobolev norm of the initial data, and you keep the t to the minus factor. And you get that if you have HS regularity, the energy decays as 1 over t to the minus s, which is exactly polynomial stability. And if you do not have any regularity, you can deduce the convergence to 0, of course, directly by Lebesgue's theorem. Okay. So for the general Lorentz media, it's more complicated. So I will just mention some of the difference, point out some of the difference. So all the p's came back, and you have in particular the presence of the zero-order term, which are responsible for some additional difficulties. And because of that, when you work with a cumulated energy density, you need another energy. You need to go to second-order time derivatives. So you have to introduce also the second-order energy that you renormalize accordingly, and you do the same for the additional energy and the damping functions. And another difference is that in the additional energy, these are the new energies in the cumulated energy, and these are new terms in the additional energy. Okay. But what does not change is that by linearity you have always this cumulated energy identity, but this time at the second order level. And the difference is in the lemma that controls the energy with the damping function. Again, there is a function which depends on k between it, but this function does not only blow up when k goes to infinity, but also when k goes to 0, because to low frequency. And this is a new factor, so that when you have to deal with this, so you have this exponential decay, and you understand that when you come back to the time domain, you have to treat differently low and high frequency, and which gives two different terms in the asymptotics, and this is the result. So you have two sets of assumptions. One is for high frequency, one is for low frequency. So the first is the same HS regularities than for Drude. And the second one is some kind of decay assumption, if you prefer. So first, some decay assumption. So for some p, strictly positive integer p, you have this weighted integrability condition. And you assume, in addition, that all moments of the initial data up to order p minus 1 vanish. Then in that case, you have this double decay in addition to the previous. Okay, so now I'm going to explain you why we can recover and improve these results using a modal approach. So I will concentrate myself to the case where all resonance frequencies are strictly positive. So same problem, simply new method. So the first thing I do is I rewrite this as a first order system, introducing a vector with capital N vector fields, where N equal 2 for the E and H, and N, E, and M as a number of elements in the Lorentz decomposition. You have 2 because of P and P dot and N. And formally, you can rewrite your evolution equation in this way with an operator, an unbounded operator, which depends on alpha. So I have made this decomposition to distinguish what corresponds to the non-undamped system and the contribution of the damping parameters. so both of them are self-adjoint. So this one is clearly the non-self-adjoint part of the operator A alpha. A0 is the one that would correspond more or less to the vacuum. No, it's not the vacuum, but to the part with alpha equals 0. It contains the curl, so it is the one which is unbounded. While the D that concerns the damping coefficient is bounded. Okay. What is classical with Maxwell's equation is that you apply this decomposition of vector fields, which is based on the fact that every L2 vector fields can be seen as a sum of a gradient plus a field with divergence free, Helmholtz decomposition. And each of these space is invariant under the action of A alpha, so you have a block decomposition of the. And the interesting case is a case where you have a really propagation which corresponds to free divergence initial data. So I will be interested by the evolution of this solution. Okay. So if you do that in the frequency domain, so using Fourier transform as before, so everything works in the same way, except that this time U is simply a vector in Cn. We are in C3 to the power n. And for each k, you have a kind of ordinary differential equations. And you have so these are no matrices of dimension 3n. The vector is of dimension 3n. So this is as before. And this, so you see that the D here does not depend on K, which corresponds to the fact that the operator is bounded, while the fact that we have this two inequality represents the fact that A0 is unbounded. For each K, you have also the decomposition of vectors into vectors which are collinear to K, which corresponds to gradients, and the orthogonals, which corresponds to free divergence field. And you have accordingly a decomposition of the matrix AAK. So you have to understand that this is as dimension 3n, this is as dimension n, and this as dimension 2n. And for each K, we have this matrix exponential to be studied. And the last very simple trick for Maxwell's equation is that you can exploit the isotropy of Maxwell's equations by remarking that the vector which are orthogonal to K as obtained from the vector which are orthogonal to, for instance, E3, only up to a rotation. And also that each A alpha K, because of this, each A alpha K is unitarily equivalent, because this is a unitary operator, to an operator that depends only on the modulus of K. So you end up with this formula. And here, because this matrix is unitary, you understand that what you have only is to understand this, so to study the spectral properties of these matrices. So when you look for the spectrum of this matrix, so it's not surprising that to see that omega is in the spectrum if and only if this dispersion relation is satisfied. Where I recall here the expression of epsilon and mu. And there are several properties that general properties about this spectrum. So the first is that all the eigenvalues have double multiplicity. So it is linked to the fact that everything, for instance, is linked to the electric field. And by polarization argument, the electric field is allowed to vary in a space which is orthogonal to K. So just a remark, all eigenvalues are multiplicity 2. these eigenvalues are continuous functions of k, which is a general theory. And you can prove that their imaginary part is strictly negative. Of course, it is not surprising from the energy decay, but it is also funny to see that it can be obtained directly from this equation by using the fact that this function here is a product of two Herglotz functions. So, for the long time decay, what matters is, of course, the behavior of the imaginary part of the eigenvalue for the energy. And as you will see, as a consequence of what I said here, you see that this imaginary part can degenerate in the sense that it can go to zero only at low or high frequency, because these are continuous functions which are strictly positive. And the fact that will happen is an obstacle to exponential stability. Okay, so the main line is of the analysis is this one. So this line it corresponds again to spatial frequency. And then you have distinguished the mid-frequency, intermediate frequency, for which the spectrum of the matrices remains far away from the real axis. And because of this, it will contribute to a uniform exponential decay of the matrix exponential, so to an exponential decay of this part of the energy. And technically, I will not come back to that, but to proving rigorously this, you use Jordan's theorem, UML formula, and compactness argument, because this set is a compact. Then the last two parts, which are the interesting parts, requires to understand how behaves the imaginary part of the eigenvalues when k goes to infinity or k goes to 0. And by understanding this, you will explain and you will quantify the polynomial stability here in terms of the regularity of the initial data, and here again in terms of the weighted integrability property and vanishing moments we have seen already. And I will concentrate myself on this part of the analysis, which is the most interesting one in my opinion. In the following, I will introduce the velocity of light. You have to probably know is defined by this. And so we want to study this equation at large k. And I will illustrate what happens in the complex plane. So since the right-hand side goes to infinity, when k goes to infinity, this must go to infinity. So either omega goes to infinity, in which case epsilon and mu goes to epsilon 0 and mu 0, and which it means that you have two branches of solutions that behave like in the vacuum as plane waves, and you can expect branch of solution like that, which could allow the imaginary part to go to 0. Either omega remains bounded, but this time it is a product epsilon mu that goes to infinity, which means that omega must tend to a pole of the product epsilon mu. And if the pole is strictly negative, this is okay. It will produce exponential decay. It will not be a problem for the analysis. But if the pole is real, and this will be possible if one of the alphas is 0, so it is in the weak dissipation case, then you will have a branch, two branches that go to 0. Okay. And again, it is authorized by the weak dissipation. So you have only to be more precise on these two behaviors. And this is where, so just a remark on the low frequency analysis, I will not do it, but it is very symmetric. When k goes to 0, either omega goes to 0, either omega goes to a 0 this time of the function. So you have a very symmetric analysis. Okay. So now this is where the heavy computations that I cannot present here are involved, and it's based essentially on Taylor expansion. It's not difficult, but implicit function theorems. But I can present the result. And just let me speak about the branches that go to infinity, and this is the results that we get. It is a high frequency expansion for large K. All the coefficients that appear here are real. So you see that the first time that an imaginary part appears is in the term is 1 over K squared. Okay. And this term here is strictly positive because I assume that at least one of the coefficients alpha is strictly positive. So it is under the weak dissipation action. Then concerning the branches that converge to a real pole. So real pole can be either simple poles, either double poles because they are a common pole of omega and mu. It may happen. So when it is a simple pole, something like that, so you have a branch, a corresponding branch. And for instance, you can assume that this pole is one of the resonance frequency with corresponding alpha 0. And you have two cases to distinguish. Either all the other, either there exists a magnetic damping coefficient which is strictly positive. In that case, again, you can prove that the imaginary part goes to 0 in 1 over K squared. And you see that this constant is strictly positive because there exists at least one alpha m which is strictly positive. So of course, this will change if all the magnetic coefficients are 0. And this is the second case. And if all the magnetic coefficients are 0, this time you obtain something in 1 over 2k to the 4. Okay. And finally, when you have a double pole, what you can prove is that it's separated in branches that separate this way. Separate first of all by their real parts. And so a double pole means that you have a common value between a resonance frequency, electric resonance and magnetic resonance with corresponding alpha 0. And again, you can prove that both imaginary parts of these two branches behaves in the same way in 1 over K squared with a strictly positive. Okay. So how to use that for the high frequency estimate of the solution? First, our asymptotic analysis shows that for large K, because of the separation and so on, the solution of the dispersion equations have exactly n simple roots. And each is associated to an eigenvector of a dimension 2. And because of this, and the dimension of the matrix is 2n, the matrix is diagonalizable. And the spectrum is made of all the branches I have presented before, and you're only that. And all of them are simples. And the ones that are an obstacle to exponential stability are this one, I'm repeating. And you can expand the solution along using the spectral projectors associated to each of these eigenvalues. And of course, to estimate the solution, in addition to the estimate of the exponential, which is related to the estimates of the imaginary part of the eigenvalues, you also need to bound the spectral projectors. And this is where it is an additional technical difficulty, because you know that for non-self-adjoint operators, the projectors are no longer orthogonal and may blow up. For instance, there is this simple example where for t equals 0, the matrix go to Jordan block, and the spectral projector may blow up in general. So we have to show that we have shown that this does not happen, and all the at least for K Leonov, all the spectral projector remains bounded away from infinity. And the proof relies on the resolvent of the matrix that we cannot compute, but we can estimate, an holomorphic functional calculus, either Cauchy formula for expressing spectral coefficients, or the fact that you can have a Lorentz series expansion of this. Okay. So, in fact, I have two or three slides to present the results, and you'll see. So, for instance, if you want to estimate the contribution of the branch that goes to infinity, first you use the asymptotics of the imaginary part of the eigenvalues to get an estimate, again, a k-dependent exponential estimate. And if you combine with a uniform bond on the spectral projector, then if you compute the contribution to large frequencies for a well-chosen M, you obtain an integral that we met in the Lyapunov approach, and then you can control as with the Lyapunov approach. Okay. So the main results are the following. So we have only the weak dissipation assumption. And you have the critical case. It is a case where, for instance, all magnetic damping coefficients are 0, and one electric damping coefficient is 0. And the non-critical case are all other cases. And the results are this one. So in the non-critical case, which is the generic case, you recover the same assumption as in the first theorem, and the same decay estimates, but this time you are able to prove that these are optimal because you can obtain also lower bounds of the same type for well-chosen initial data. And in the critical case, it seems to be the same, except that you see that the decay is slower, is divided by 2. It is a consequence of the 1 over K4 that comes in the asymptotics of one of the eigenvectors. And probably I will stop here. Prefer. If there is a question corresponding to the slide here, it will be okay.